Hello chemists, this is Ms. Placino and you're watching lesson 10.1 on types of mixtures. In today's lesson we're going to be looking at different types of mixtures and how to differentiate between them. Goals for today's lesson. You should be able to identify the basic components of a solution, so just a little bit of terminology, likely going to be a review for a lot of you. Classify different homogeneous mixtures. We're going to be focusing on solutions, but there are other ones out there that you should be familiar with. And we'll differentiate between electrolytes and non-electrolytes, really building on a topic that we first addressed in Unit 7. Let's get started. I want to start off by looking at solutions. A solution is a homogeneous mixture composed of two or more substances. Solutions have to be homogeneous. They have to be the same throughout or uniform. We're going to be focusing on pretty simple solutions consisting exclusively of just two substances. A good example of a solution might be salt and water or sugar and water. You know from experience that you can stir that mixture and you can make it completely homogeneous. No evidence that salt or sugar has been added. Solutions tend to have extremely small particles present on the size of atoms, ions, or molecules. So salt will break up into ions. Something like table sugar, sucrose, is going to stay as a molecule that is possible to dissolve individual atoms in as a solution. One of the other keys for a solution is that it's not going to separate on standing. And if you take your salt water and you just leave it sitting out for a while, the salt isn't going to spontaneously come out of solution. It's going to stay homogeneous. Just kind of moving on with some definitions. Solute and solvent are going to be the two components of a mixture. So when we talk about the solute, we're talking about the material that is getting dissolved. Often it's going to be a solid. When we're in the lab, for example, especially at this level of chemistry, our solutions will almost always consist of a solid solute. You've got to dissolve that solute in something. That material is referred to as the solvent. Many times, the solvent is going to be a liquid. Often, again, when we're in the lab, it will probably be water. It is possible to have solutes and solvents in any phases, really. For example, an alloy has a solid solute and a solid solvent, and to try to differentiate between the two at that point in time, just the solute would be the material that is present in smaller quantities, the solvent, the material that's present in larger quantities. What we're really going to focus on, though, is solid solutes dissolved in liquid solvents. So just to kind of give you a visual, you've got your solvent, again, many times it'll be water, and then we're going to just dissolve our solute in the solvent. Not every material will dissolve in the solvent. So I want to talk a little bit about predicting solubility. And this is something that we've done to a certain extent already. Back in Unit 5 when we're trying to predict the products of double replacement reactions. So just kind of bear with me as we do a little review. When we talk about a material being soluble, that means that it is able to dissolve in the solvent. For example, salt is soluble in water. You can form that homogeneous mixture. Insoluble means not able to dissolve in the solvent. If I was to take something like oil and try to dissolve that in water, you know from experience that oil and water will not mix in one another. So oil is largely insoluble in water. When it comes to predicting solubility, we use this phrase, likes dissolve likes, in chemistry. And what we're referring to when we say likes dissolve likes is the substance's polarity. In order for substances to dissolve in one another or to form this homogeneous mixture, this solution, they must have the same polarity. Polarity is a topic that often gives students fits as they're learning chemistry, so I want to take just a couple minutes to review what polarity is. All right, so needless to say, I'm over in the notes now. For substances to be soluble, they must have the same polarity. And again, we say likes, dissolve, likes. So hopefully you remember that a substance, I should be more specific, a covalently bonded molecule can be either polar or nonpolar. When we think about polar molecules, water is an excellent example of a polar molecule. So I'm going to go ahead and just draw the Lewis structure for water. The definition of a polar molecule is just uneven or unequal charge distribution. You might remember that oxygen is a fairly electronegative atom. Hydrogen, not so much. So in these covalent bonds between the hydrogen and oxygen atom, oxygen is going to be pulling the electron density towards itself in both cases, making it slightly negative and leaving the hydrogen side of the molecule slightly positive. That means that water molecules are able to behave like little magnets. You can imagine the negative end of one water molecule being attracted to the positive end of the other. If we just kind of look at some characteristics of that Lewis structure, on the central atom, on oxygen, we see that we've got some unshared electron pairs. Those two sets of dots on oxygen are unshared electron pairs. And if we want to look at symmetry, we only see one line of symmetry here, so polar molecules tend to be not very symmetrical. Symmetry is not a foolproof method of gauging polarity, but in most small molecules it works out pretty well. If you have to envision a nonpolar molecule, maybe something like methane is coming to mind. CH4. Nonpolar molecules, by definition, have an even or an equal charge distribution. So instead of seeing that positive and negative side of the molecule like we have over in water, we kind of have just the same charge throughout the methane molecule. We don't see any unshared electrons pairs. And that's kind of a general rule of thumb for nonpolar molecules. And if you were to try to look at the symmetry on this molecule, you can fold it in half along a number of different axes. So I would say that this molecule is highly symmetrical. Again, symmetry not always the best tool to evaluate polarity, but often it will lead you down the right path. Okay, so let's do a little bit of practice with this idea of polarity. Go ahead and flip over to your practice problems. So in question 1, you're asked to predict the polarity of each molecule and determine whether a solution would form. So this first one, we've got water, H2O, and ammonia, NH3. You might be to the point where you can kind of just visualize these molecules in your head without sketching them out. I'm going to go ahead and draw them just to make sure we're all on the same page. Hopefully water is one that you don't have to do too much thinking on. Also, we just drew it. Ammonia is NH3. Am I done? Careful, I haven't completed the octet. Remember, ammonia and most nitrogen compounds will have nitrogen with those two unshared electrons present. Make sure you draw them. If I've got to assess the polarity of these molecules, water is of course polar, we just spoke about it. Ammonia, I've got an unshared pair of electrons on my central atom, not particularly symmetrical. That's going to leave ammonia to be polar as well. And since they're both polars and likes dissolve likes, a solution will form. Go ahead and try out questions B and C on your own. I'm going to have the answers kind of just appear, so pause the video, figure them out, and check your work. All right, so I've gone ahead and I've drawn the Lewis structures for the molecules present in B and C. Silicon tetrachloride, highly symmetrical, no unshared pairs. This is likely a nonpolar. Water is going to be polar. I've got nonpolar plus polar, so if I try to mix these two together, they're going to separate out the way oil and water do. So no solution will form here. Silicon hexafluoride and ammonia. I know ammonia is polar. Sulfur hexafluoride, I see high degrees of symmetry, no unshared pairs, probably nonpolar. So again, I should not see a solution form in this case. You have to have the same polarities in order to get a solution to form. Hopefully, this kind of helped you just review polarity, maybe drawing some Lewis structures, and you're getting the hang of it. Let's get back to the notes. I want to talk more about classifying mixtures. Now, most of what we look at this unit will be solutions, those homogeneous mixtures we just spoke about. But in addition to solutions, we also have something called suspensions. Suspensions, you can kind of think about one of those snow globe things. If you take the snow globe and you shake it up, You make a fairly homogeneous mixture. Over time, those snowflakes are going to fall, kind of settle at the bottom of the snow globe. A suspension is just that. You've got a mixture that contains large solute particles that will settle unless constantly stirred. Sure, you can keep that snow globe homogeneous if you're willing to sit there and constantly shake it and keep agitating it to keep it mixed. But once you stop agitating the mixture, those particles are too big to stay evenly distributed through the solvent, so they're going to settle out. Another good example of this is just sand and water. Kind of the same idea. You can shake up that mixture, you can make it homogeneous for a period of time, but ultimately the particles, in this case the sand, the solute really, is just too big and it's going to come out of solution. Actually, I shouldn't even say that. It's going to no longer be homogeneous if not constantly agitated. Colloidal dispersions, or just simply colloids, are kind of the middle, medium size between solutions and suspensions. When you have particles that are too big to technically be considered a solution, but too small to be considered a suspension as your solute, you've created a colloid or a colloidal dispersion. We come in contact with these all the time in the real world. Something like smoke. The particles, like the ash that actually makes the smoke, those are too big to be considered a solution. It's not homogeneous, you can see them, but they're going to stay dispersed for a pretty long time, so it's not really a suspension either. Something like shaving creams and whipped creams, you've got different proteins and fats kind of in this mixture. Mayonnaise, same idea, something like butter, and you have colloidal dispersions. So a lot of products that you just come in contact with on a regular basis in your everyday life are colloids. You might be wondering, if they're able to stay kind of homogeneous, how do we differentiate between a colloid and a solution? Well, I'm very glad you asked. We use something called the Tyndall Effect. Have you ever watched one of those heist movies, like where the criminals are trying to steal something like a piece of artwork or maybe a rare jewel? And inevitably, these priceless artifacts are protected by lasers. And you can't see the lasers because, they can't see them through air. They've got to hit a wall or something. And then the criminal is going to pull out some sort of magic can of spray and kind of spray it through the room. And then suddenly those laser beams are exposed and they can deftly dodge them so that they can steal the artwork or the jewel or whatever it is. You might be wondering, well, where does one get that magic bad guy spray can of laser defeating material? And the truth is, something like chalk dust would work, hairspray would work, because it's taking advantage of this Tyndall effect. The Tyndall effect is really just the scattering of light by small particles. My guess is you played with a laser pointer in the past, and if you shine it through the air, you're not going to be able to see the beam of light until it hits the wall, and you've got that one dot on the wall. That is because air is a solution. Let me draw. There we go. A solution is the same throughout with really, really small particles. You cannot see the beam of light through a solution. In a colloid, like those medium-sized particles, and I know that is super, super vague and subjective, but you've got particles that are big enough where they're going to be able to scatter the light. So all you really need to do if you wanted to expose a laser beam is to hit it with a colloid. Something like smoke does the job. Again, hairspray, chalk dust, anything where we've got small enough particles where they can kind of stay distributed through, in that case, the air, but they're big enough where they're able to start to scatter this light. So again, we're going to observe it in the colloid. So we'll see the beam. And it's not observed in the solution. So you cannot see the beam. I think always kind of a fun fact about how to differentiate between the two. The last thing I want to wrap up with today is kind of revisiting the idea of electrolytic and non-electrolytic solutions. So let's head back to the notes. All right, so here I want to test 4 different solutions for conductivity. We'll be looking at pure water, so just the solvent, 0.1 molar sodium chloride, 0.1 molar sucrose, and 0.1 molar calcium chloride. I know I haven't talked about what that capital italicized M means. Since they're all the same, this stands for molar or molarity, and this is just telling us that we're working with the same concentration in terms of moles of solute per liters of solution of those 3 substances. So what I'd like you to do first is to go through and let's make a couple predictions based on which solutions will conduct or not and be able to explain your answer. Then we're going to go back and draw what we think we'd see on a molecular level for these 4, well, I guess 1 substance and 3 solutions. All right, so when it comes to pure water, will it conduct? Hopefully you're thinking no. We've done this demonstration before. Pure water is not conductive. Do you remember why not? Yeah, it's a non-electrolyte because it does not produce ions, at least no appreciable amount of ions. We know we need those ions to conduct electricity. What about sodium chloride? Yeah, this one's conductive. Why? We're going to make Na plus and Cl minus ions. Don't be intimidated by that big formula for sucrose. Sucrose is just table sugar. We did that in a demonstration as well. It's also not conductive because no ions form. Something like sucrose or any other covalently bonded molecule, the molecule will just be surrounded by the water molecules. It'll effectively just get wet, but it does not break apart. And finally, calcium chloride. Yeah, you're probably thinking that one's conductive as well. We're going to make calcium and chloride ions. So if we go back and just kind of draw what we'd see. Pure water, of course, we're just going to have the H2O molecules floating around. And something like sodium chloride, we know that we'll make a sodium ion and a chloride ion. Every time a sodium chloride breaks apart. So I just drew a total of 3 sodium chlorides dissociating or breaking apart into ions. I'm going to represent my sucrose molecules with just that like kind of red circle thing. They won't break apart. I'll just have sugar molecules floating through solution. And finally, calcium chloride. Every time it breaks apart, I'll produce a calcium and 2 chloride ions. Okay, so hopefully that is just kind of review from things we've already spoken about. If you had to make a prediction about which of these 2, the sodium chloride or the calcium chloride, would be more conductive, which one would you choose and why? Pause the video, think about it, and we'll talk when you come back. All right, so we know that both sodium chloride and calcium chloride solutions will be conductive, but which one will conduct more electricity? If you're kind of stuck on this one, look at the 2 pictures that you drew for the 0.1 molar sodium and 0.1 molar calcium chlorides. You've got ions in both, but what do you notice is different about those 2? Okay, yeah, we've got different cations present with different charges. What else? Yeah, we have different numbers of ions. Calcium chloride, when it dissociates or breaks apart, it forms a total of 3 ions, a calcium and 2 chloride, while sodium chloride only forms 2 ions, a sodium and a chloride. Calcium chloride will be more conductive at the same concentration. So I'm going to write it as a higher conductivity. due to more ions. Let's move that up. In solution. So if we were using the conductivity meter, or kind of that light bulb apparatus that we had set up previously, we would see the light bulb glowing more brightly in the calcium chloride solution than in the sodium chloride solution. Even though they're technically the same concentration, 0.1 molar, they've got the same number of moles per liter, because calcium chloride breaks down into more ions, we're going to see greater conductivity from that solution than we will the sodium chloride solution. All right. I know I'm running a little long today, so I want to wrap it up, but a good question to practice with on this one would be question number 3, so that you can kind of review writing those dissociation equations and start to make some predictions based on the number of ions present, which will be the most and the least conductive of those solutions. All right, chemists, we're going to wrap it up there for today. Thank you for tuning in, and I hope you found this helpful.